Good morning. I am Prasannanjaneya Reddy, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. In this session, we are going to discuss about the ARM processor architecture. Particular model is TM4C123GH6PM. For this session reference is textbook is Introduction to Embedded System by Shubhu KV, and we need to follow the data sheet, that is TM4C123GH6PM data sheet. This is the reference purpose. First, ARM. ARM means Advanced Risk Machines. Means that processor architecture provides the reduced instruction set computing elements. So ARM Holding is a company. They are manufacturing different types of processor architectures. One of the processor architecture is ARM Cortex-M. Here I am indicating this processor architecture is used in the microcontroller design. So different examples of this Cortex-M are Cortex-M0, M0 Plus, M1, M3, 4, 7, 23, 33, 35P. These are the different examples for ARM Cortex-M processor architecture. If you look at this architecture, this is a generalized architecture. In this architecture, first it contains processor core for executing the instructions. Next, it contains memory devices, RAM and RAM for storing the instructions and data. And it contains various input ports for getting the current information from various input devices like sensors, keyboard, touch screen, switches. And various output peripherals for monitoring like display devices and for controlling like actuators. Okay, and additional hardware for doing the desired operation like analog to digital conversion, digital to analog conversion. For providing accurate timing reference, it uses real-time clock. Like that, it contains various additional hardware circuits or internal peripherals. And it contains various buses for sharing the information among all these elements of the design. Like it contains I code bus. I means instruction. It fetches the instruction from the flash memory. Similarly, D code bus. D means data. It fetches the data from this flash memory. And system bus. The system bus is interacting with the input ports, output ports and RAM. And advanced high performance bus is used for doing the high speed operations like read and write from the USB peripherals, either 1 Mbps speed data rate. And private peripheral bus. These communication buses are used for interacting with the additional hardware circuit that is used in this design. So, ARM Cortex-M series architecture contains 32-bit RISC processor. means that bus width is 32 bits. It will process the data, 30-bit data or 32-bit instructions at a time in a single clock cycle. Since it contains 32-bit bus width, it can interface with up to 2 power 32 bytes, 32 bits memory locations. 2 power 32 means 4 gigabyte memory. Okay. Next. This processor architecture supports 3-stage pipelining. So what is the pipelining? Means parallelly do the multiple operations. In a single clock cycle, we can fetch the third instruction, decode the second instruction, execute the first instruction. Why? Because embedded systems has deadlines. If the deadline missing means we may loss of life or properties. So to meet the deadline, we need to provide accurate timing reference. Okay. If you want to provide accurate timing reference means we can do the operations parallelly to reduce the execution time. Execution time reducing means automatically improve the speed. So here Cortex M4 series processor supports 3-stage pipelining. So fetch the instruction, decode the instruction, execute the instruction at the same time for different instructions. Next, this Cortex M4 series architecture supports the Harvard based processor architecture. Means the processor has separate buses for fetching the instructions as well as data. Okay. So it contains various buses, I-code bus, which fetch the instructions from flash memory, decode bus, read constant data from the ROM, system bus, it performs read and write operations from RAM and IO ports, private peripheral bus, do the read and write operations from internal peripherals, and advanced high speed bus or high performance bus that performs the read and write data from high speed peripherals like universal serial bus. So it contains nested vector interrupt controller. Interrupts means disturbance or interrupt indicating some external task is waiting for CPU for doing its operation. Okay. So while managing the interrupts, if we are reducing the interrupts delay as possible, we can meet the deadlines. As the interrupt latency means interrupt delay increases, the task may take some time delay to meet the deadline. Automatically, the deadline delay means we can miss the deadlines. Missing of deadline may cause loss of life or properties. So, this ARM Cortex M4F series processor architecture provides tight integrated nested vector interrupt controller. It will reduce the interrupt delay as possible by efficiently scheduling the interrupts. So it communicates with private peripherals by using private peripheral bus. The tight integration of the processor and interrupt controller provides fast execution of interrupt service routines, dramatically reducing the interrupt latency. So interrupt service routine means, so after occurring interrupt, what it will do, that is defined in the form of instructions. That group of instructions we call interrupt service routine. Okay. So we can avoid the delay for executing the interrupts and meet the deadline within the time by using this nested vector interrupt controller. If you look at the register organization of ARM processor architecture, so it contains various types of registers. Some of them are, it contains R0 to R15 registers, total 16 32-bit registers. Among them, R0 to R12 are used for storing the data and instructions as general purpose registers. The register size is 32 bits. Coming to the R13 register, it's used for stack pointer. Pointing means address. So it stores the address of the stack top. Here two types of stack pointers. One is main stack pointer. Another one is process stack pointer. Main stack pointer deals with the exceptions while executing the instructions. Exceptions means anything divided by 0. In denominator, 0 means that value that contains infinite information. So that is invalid. So this main stack pointer dealing with the exceptions raised while doing the operations. Process stack pointer deals with the normal execution. Next, link register R14 register is used for link register, means it stores the written address of the instruction. Next, R15 is used as program counter. Program counter fetch the address of the next executed instruction. So, total 16 registers. Among them, 13 registers are used as general purpose registers. R13 register used for stack pointer, for dealing with main stack pointer, means exceptions raised during the operation, as well as normal execution. Link register stores the written address of the instruction. Next, program counter fetch the address of the next executed instruction. Next, it contains some special function registers. Those are program status registers. Again, in this, primary mask register, fault mask register, base priority register, and next control registers. Okay. Here mask means hiding. So while doing the operations, if you want to stop the interrupts, or if you are not interested to allow the interrupts while executing high priority or some other tasks based on the requirement, at that time we can use this mask registers. We will check one by one. So R0 to R12, those are used for storing the data or addresses like general purpose registers. R13 for storing the address of stack top of address. Link register stores the written address of the functions and ISR. Program counter fetch the address of the next executed instruction. Next, primary mask registers, that is used to mask, means hiding the interrupts and exceptions. Fault mask register used to mask the interrupts and faults. These are occurred while doing the operations. Base priority register, it defines the priority of the executing software. It prevents the lower priority and equal priority tasks and allows only highest priority tasks. So, by default, we are allowing all the interrupts, exceptions and faults. Whenever in particular condition, if you want to stop the interrupts at that time based on the type of interrupt, we can use by enabling corresponding bit position. Suppose primary mask register used to mask the interrupts and exceptions. If you want to don't allow the interrupts at that time, the primary mask bit will be 1. By default it is 0, means it allows all the interrupts and exceptions. Whenever we want to stop that interrupts and exceptions, we need to give the interrupt mask bit is 1. Similarly, by default it allows faults and interrupts by default. That at that time the value is 0. Whenever we want to stop or hide the fault interrupts, at that time this fault mask bit is 1. Next, similarly base priority. By default it allows all the interrupts. Whenever you want to allow only highest priority task, this value is 1. So there are 3 status registers. Those are application program status register, interrupt program status register, execution program status register. These are accessed individually or in combination of program status register. We will check it once. First one is application program status register. Okay. In this is a 32-bit register. In this 0 to 26 bits are reserved for future purpose. 27th bit indicating saturation. By default all the values are this flag register are zeros. Whenever after performing the operation, if the result saturation occur, means this Q value is 1. Q means saturation. Next, in the result overflow occurs after doing the operations. If the result is size is more than the defined size, means overflow occurs. At that time this overflow flag value is 1. Next, in the result, if the carry is generated after performing the operation, that carry flag is 1. In the result, if the result is 0 after doing the operation, the result is 0, means this 0 flag is 1. If the result is negative, means negative flag is 1. Okay. By default all the flags are 0. Whenever we are getting this type of results, that flag corresponding flag bit will be 1. After performing the operation, if the result is saturated, the saturation flag is 1. If the result is overflow occurs, overflow bit is 1. If the result carry is generating, carry flag is 1. If the result is 0, 0 flag is 1. If result is negative, negative flag is 1. Like that. Next, interrupt program status register. Here 0 to 8 means total 9 bits. This contains interrupt service routine number. So which interrupt is executing here? Okay, ISR number. So 9 to 31 bits are reserved for future purpose. Next, execution program status register. Here 0 to 9 bits are reserved for future purpose. 10 to 15 bits are used for interrupt and continuous execution or if then instructions. Suppose we are having multiple interrupts. While doing the execution, if the interrupt is paused for some duration, next if you want to continue that one, we are giving 1. Okay, in the nested vector interrupt controller, we can use this one. So by combining these 3 status registers, we can call program status register. We can use this one. Okay. So APSR, application program status register, contains conditional flags, which gives the information about the result of a previous arithmetic and logical unit operation. So n is set to 1 means the result of the operation is negative. 0 flag is set to 1 means the result of the operation is 0. Carry flag is set to 1 means the carry is generated in unsigned addition or subtraction. If overflow flag is set to 1 means if a signed operation overflow occurs. Saturation flag is set to 1 means if the result of an operation exceeds the register capacity. The Q bit indicates the saturation has occurred. Interrupt program status register contains ISR number which is being handled by the processor. So, which interrupt is accepted and corresponding ISR number is available in the interrupt program status register. Next, execution program status register contains the mode control bits. The T bit indicating thumb instruction set. So, it supports the thumb instructions. The ICI and IT interrupt and continue its execution or if then instruction bits are used by the interrupts and by the if then instructions. So this is the particular ARM processor architecture. That model number is Tiva series TM4C123GH6PM. So TM indicating Texas machines, 4C indicating series. Okay. So 1, 2, 3 indicating corresponding memory capacities. So like that, each variable has particular meaning in this model number. Coming to the architecture, first it contains 80, this processor name is ARM Cortex M4F. Advanced RISC machines, Cortex M indicating that is this processor architecture for microcontroller based applications. F indicating it is doing the floating point operations. Means 0.1234 point fraction of values operations. Its clock frequency is 80 megahertz. So it provides that much of speed. Next, it contains 256 bytes flash memory, 32 kilobytes static random access memory, and it contains ROM for storing the bootloader, driver library files, advanced encryption system code, cyclic redundancy code. Okay, first processor, that is ARM Cortex M4F. It will do the floating point operations. Coming to the memory, it contains 32 kilobytes static random access memory, 256 kilobytes flash memory, and it contains read-only memory for storing the bootloader, driver library files, advanced encryption system files, as well as cyclic redundancy code. Next, it contains 43 general purpose input and output pins or output lines. So as the number of pins increases, it will interact with the more number of devices to provide more number of features. Next, coming to the additional hardware circuits, it contains two watchdog timers within the chip. So watchdog timer is used for monitoring the CPU continuously with some predefined time. Later, if the system is hang out, means it generates the reset signal. Okay. Next, it contains on-chip DMA controller, direct memory access controller. So, without CPU interaction, it will perform the read and write operations with the external memory devices to speed up the operation and for efficiently utilizing the central processing unit. And it contains system control and clocks, precise oscillator, and it contains on-chip joint test action group and serial wired debugging device. It contains on-chip embedded trace macro cell. It contains on-chip floating point unit for doing the floating point operations, macro cell for debugging the instructions, and it contains nested vector interrupt controller for efficiently managing and scheduling the interrupts, thereby reducing the interrupt latency and improve the speed. Next, it contains memory protection unit to avoid the unauthorized accesses. For that purpose, it provides the security memory protection unit. Okay. Next, it contains 2 kilobytes E2P. It contains hibernation module. Hibernation module for saving the power consumption by disabling the power supply to the unused components. It contains 12 general purpose timers for providing the accurate timing reference. Next, it contains 12-bit ADC. Bus width is 12-bit. Okay, analog to digital converter channels. It contains 2 analog comparators, 16 pulse width modulators, 2 quadrature encoder interface modules, and it contains 2 CAN node controllers, 4 I2C inter-integrated circuits, 8 universal asynchronous receiver and transmitters, 4 synchronous serial interface modules, USB port with advanced high peripheral bus and high performance buses for sharing the information among like these devices. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.